Section 4-2 is on the derivative of a product of two functions. The objective here is given a function that is a product of two other functions. Find an equation for the derivative function. All right, so let's take a look at the rule here. This is known as product rule, named because, of course, we're taking the derivative of a product of two functions. Now, there's a couple ways that we can write this rule. I'm going to write it this first way here in the form that we've seen before, where we use function notation to write it. And the rule is this. It says if f of x is equal to g of x times h of x, there's the product of two functions. Notice that's not a composition. It's not g of h of x. It's g of x times h of x. So if f of x is the product of g and h, then f prime of x is the following. It's equal to the derivative of the first function, g prime of x, times the second function, h of x, plus the first function, g of x, times the derivative of the second function, h prime of x. In fact, we sometimes read that derivative off there as the derivative of the first times the second, plus the first times the derivative of the second, where first and second there are representing your first and second functions in your product. So that's our derivative of a product. Notice it's not the derivative of the first function times the derivative of the second function to find the derivative of a product. It's a common mistake, and it's got more to it here. The other way that we could write that in terms of u and v, it's a little bit cleaner to write it this way, I guess. A little faster way to remember perhaps the rule, as well as a little bit faster way to write it down. But if y is equal to u times v, where u and v are two functions, then y prime is equal to u prime times v plus u times v prime. So it doesn't matter which one of those two you remember. Obviously, it's important that you remember one of them. But in both cases, you're taking the derivative of the first function times the second function, and then adding to that the first function times the derivative of the second function. All right, so let's look at why that is the case. We're going to go back to the proof of this, actually, and actually prove that this is, in fact, the rule. We're going to use that first form that we wrote this in. So just like you've seen before, whenever we're trying to prove a theorem, if we're doing it directly, then we just start out with the conditions of that theorem. So the first thing that we have here is we're going to let f of x be equal to the product of g of x and h of x. And we want to show what f prime of x is equal to. So we're going to go back to our formal definition of a derivative, which is that limit as h goes to 0 is usually what we write, but because we have a function here called h, I'm going to use the second form of this, where we say delta x goes to 0 instead of h going to 0, just so we don't confuse that value h going to 0 with the function h of x. And then it's f of x plus delta x minus f of x all over delta x. So it's that limit of that forward difference quotient is what we have there. All right, so the first step of this is to substitute what function f is equal to. So we've got the limit as delta x goes to 0 of f of x plus delta x. That means I'm going to take the x plus delta x and replace the x's in this function with x plus delta x. So it's going to be g of x plus delta x times h of x plus delta x, and then minus, do the same thing with f of x, replace it with what it's equal to. That's equal to g of x times h of x. And again, this is all divided by delta x. All right. Now, this next step here involves adding in what we call a clever form of 0. We've seen how we can multiply by a clever form of 0, or excuse me, a clever form of 1, which means you're multiplying by a fraction whose numerator is equal to the denominator, and thus that fraction or that quotient is equal to 1. And of course, multiplying by 1 won't change the problem. The same is true if we add a clever form of 0. Of course, adding 0 to anything doesn't change the problem. And all that means is we're going to take some value, add it into this problem, and then later subtract it back out. Okay, so in other words, we get a clever form of 0 that way. So let's start out with our limit notation here. We have the limit as delta x goes to 0. We're going to leave that first part alone there. G of x plus delta x times h of x plus delta x. And I want to actually I'm going to subtract this clever form of 0 first, and then I'm going to add it back in, is the order that I'm going to do it in. But you've got minus g of x times h of x plus delta x. That's the value we're going to subtract out. And so that the problem doesn't change, we're going to add that right back in, plus g of x times h of x plus delta x. I'm running out of room here, so let me scoot this over here. Select that and just slide it over. And then we still have the very last part of our previous step there. We still have to subtract the g of x times h of x. G of x times h of x. Just barely fits there on that line. But this is all divided by delta x still. So again, in the middle there, you can see that I've subtracted some quantity, but then I added it right back in. That's my clever form of 0 right there. Now, what I want to do is actually group these together. I've written them in this order for a reason. I want to group these together just like this. I want to take these first two terms and group them together. And I want to take the last two terms and we're going to group those together. That's the reason why I've written it that way. And in fact, what I want to do is split this into two separate fractions here, two separate quotients. So we're going to do that here in the next step. This is equal to the limit as delta x goes to 0 of the following. It's going to be g of x plus delta x times h of x plus delta x minus g of x times h of x plus delta x. I'm going to write that all over delta x. And then we'll add on the second half of this, which is g of x times h of x plus delta x, and then minus g of x times h of x. And that's all over delta x. And that's what we're taking the limit of. So I've split that up into two separate fractions. Of course, since they have a common denominator, if we added these together, the denominator would stay the same, but the numerator would, of course, be the sum of those two. We'd have what we started with. And now what I have here is actually the limit of a sum of two quantities here, two functions. So we know that from our properties of limits that the limit of a sum is equal to the sum of the limit. So I'm going to use that property there to rewrite this as the limit as delta x goes to 0 of g of x plus delta x times h of x plus delta x minus g of x times h of x plus delta x. And that's all over delta x. That's the limit of the first function plus the limit as delta x goes to 0 of the second function here, g of x times h of x plus delta x minus g of x times h of x. And that's all divided by delta x. The limit of a sum is equal to the sum of the limits, is that property that we just used there. And now I see that in the first limit, in the numerator, I've got an h of x plus delta x in the first term, and I've got the same thing in the second term. So I'm going to actually factor that out. So let's rewrite this. This is the limit as delta x goes to 0 of g of x plus delta x minus g of x. That's all over delta x. I'm going to put that factor that I'm factoring out there out to the right of this fraction here. So it's times h of x plus delta x. And then in the second limit that I have here, I can see that I've got a g of x in the first term in the numerator, and I've got another g of x in the second term in the numerator. So I'm going to factor that out. So I've got the limit as delta x goes to 0. I'll factor the g of x out front times the quotient here, h of x plus delta x minus h of x all over delta x. And now what I have here is I've got the limit of a product plus another limit of a product. So I can actually use my product properties here. If I have a limit of a product, that's the same as the product of the limits. So we're going to break this up one more time here, and I'll have the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x times the limit as delta x goes to 0 of h of x plus delta x. And we'll add that to, again, we have another limit of a product here, so that's equal to the product of the limits. So the limit as delta x goes to 0 of g of x times the limit as delta x goes to 0 of h of x plus delta x minus h of x all over delta x. And now we're actually ready to evaluate these limits and see what we're looking for. If you notice now we've got it as a product of two things first plus the product of two other things. That's looking quite a bit like product rule that we had written down up above. But if we look carefully at what we've got here, I've got the limit of a difference quotient, the limit of a forward difference quotient for function g. And by definition, the limit of this forward difference quotient of g is called g prime of x. And then the next limit that you have just h plus, h of x plus delta x. So as delta x goes to 0 there, you'll have just h of x because the delta x is going to 0. And then we're adding that to, we have the limit as delta x goes to 0 of g of x, which there's no delta x in there at all, so it's just going to give us g of x. And finally, at the end, we have another limit of a forward difference quotient for function h this time. So by definition, the limit of a forward difference quotient for function h is defined as h prime of x. So we've proven then that the derivative of function f turns out to be equal to g prime of x times h of x plus g of x times h prime of x. That right there is our product rule. All right, so let's try using the product rule in a few examples. If you take a look there at example 1, they give us y is equal to this product. It's x to the 4th times the cosine of 6x. And they want us to find dy dx. That's a way of writing the derivative of this function. So if we want to find dy dx, again, the thing to notice here is that I've got a product of two functions. I've got x to the 4th, and I've got the cosine of 6x. It's the product of those two, so I know I've got to follow product rule. So the rule is I take the derivative of the first function, derivative of x to the 4th is 4x cubed, and I multiply it by the second function, cosine of 6x. And then I add to it the first function, which is x to the 4th, times the derivative of the second function, which the second function is actually a composite function. Cosine is the outside function, 6x is the inside function. So use chain rule here. So chain rule says you take the derivative of the outside function, which is a negative sign, and then chain rule says you substitute in the inside function there, the 6x, and finally you multiply that by the derivative of the inside function. That would be the 6. And let's just rewrite this here slightly. Combine your constants, and if there's anything else that we can obviously do, we'll also combine those things. But I see I've got 4x cubed, cosine of 6x. There's nothing really I can do with that. And then I've got plus, actually I'll make that a minus here because I got a negative sign. So I've got minus 6x to the 4th sine of 6x. And you can leave it right like that in that form there. All right, let's take a look at another example. Example 2. It says if y is equal to this function right here, y is equal to 3x minus 8 raised to the 7th power times 4x plus 9 raised to the 5th power. It says find y prime and simplify. All right, so y prime. Again, the key here to recognize is that you've got a product of two functions. Here's my first function, and I'm multiplying that by this second function. So because it's a product of two functions, I've got to use product rule. Product rule says take the derivative of the first function. Now the first function, again, is a composite function here. 3x minus 8 is the inside function. The 7th power is the outside function. So because it's a composite function, follow chain rule. Chain rule says you take the derivative of the outside function, which is 7 times something to the 6th power. And then chain rule says we substitute in the inside function, 3x minus 8. And then finally, we multiply by the derivative of the inside, which is 3. There's the derivative of the first function. We then multiply that by the second function, 4x plus 9 to the 5th power. We'll add that to the first function, 3x minus 8 to the 7th power, times the derivative of the second function. Again, the second function here is a composite function, so follow chain rule. Chain rule says take the derivative of the outside function, which is going to be 5 times something to the 4th power. Then chain rule says you substitute in the inside function, the 4x plus 9. And finally, chain rule says you multiply by the derivative of the inside, which is 4. And let's combine some things here. I'm going to write this actually in a couple of forms here for you. In the first term of this, I see I've got 7 times 3, so I'll put that as 21 times 3x minus 8 to the 6th times 4x plus 9 to the 5th. And in the second term, I've got 5 times 4, that's 20 times 3x minus 8 to the 7th times 4x plus 9 to the 4th. There's our derivative function. Now, you can leave your answer just like that. You don't need to go any further with this. However, some of the problems in the book, and in fact, even if this example, they're going to go a little bit further with this. And I can see that I have a factor of 3x minus 8. I have 6 of them, actually, in the first term. And I have a factor of 3x minus 8. I have 7 of them, actually, in the second term. So I could factor those guys out. We're going to do it that way. I've got 3x minus 8. I've got 6 of them in the first term and 7 in the second term, so I can factor out 6 of them. And if I look a little bit closer, I see that I've got 4x plus 9 in the first term, and a factor of 4x plus 9 in the second term. I've got 5 of them in the first term, 4 of them in the second term. That is, it's raised to the 5th power and the 4th power, respectively. So I can factor out 4 of those, 4x plus 9 to the 4th. And now let's write down what's left once I factor out or divide those out. I'm still left within the first term there, the 21's still there. I factored out 6 of the 3x minus 8s, and that was all of them. That's all I had. I factored out only 4 of the 4x plus 9s. I had 5 of them, so there's still 1 of those left. 21 times 4x plus 9. And we'll add that to the 20 is still there. We didn't factor any constant, which, by the way, you could factor out constants if you had common factors there. Between 21 and 20, though, there's no common factors. So that's why we didn't touch those. I factored out 6 of the 3x minus 8s, but I had 7 of them, so I still have 1 of the 3x minus 8s. I had 4 of the 4x plus 9s, and I factored out all 4 of them, so they're all gone. And if you look at what you have in that last set of parentheses, that's actually a linear function. If we rewrite this slightly, we'll see that. You've got 21 times 4x, which is 84x. And you've got 20 times 3x, which is 60x. So 84 and 60 should give us 144x. And I've also got 21 times 9, which would be 189. And I've got a minus, because it's negative here, the negative 8. I've got a minus 20 times 8, that's a negative 160. So 189 minus 160 should give me 29, I think, as a result of that. And so there's another form that you could write this in. Again, it's sufficient to leave it in that form that I said earlier where I've underlined these. In fact, I'll put a little star by this. This form right here is fine to leave it in. But if you're trying to figure out what has the book done or how do they get their answer in the back, they've taken these extra steps to get there. Okay, so you definitely would need to get those or do those extra steps if you wanted to compare your answer. All right, let's take a look at one last example here. Example 3 says if y is equal to e to the sine of x, and they want us to find d squared y dx squared. So they want me to find the second derivative. So if you look at this, be careful, because just because we're in the section on product rule doesn't necessarily mean you're going to use product rule here. There is no product. This is a composition. This is e raised to the sine of x. So e is the outside function, sine of x is the inside function. Follow chain rule. Chain rule says take the derivative of the outside function, which is e raised to some power, and then substitute in the inside function, that would be the sine of x, and then finally multiply by the derivative of sine of x. Derivative of sine, of course, is cosine of x. So there's the first derivative. It's just, I guess I don't know which way you want to write this. It doesn't really matter whether you put the exponential function first or the cosine function first. I'm just going to rewrite it without the parentheses. You don't really have to do that, I guess. But there we go. There's our derivative, e to the sine of x times cosine of x. And here's why this is in this section then, because they want the second derivative. And I can see now I have a product of two functions. So d squared y dx squared, it's a product of two functions. I've got e to the sine x and I've got cosine of x. I'm multiplying those two together, so I've got to follow product rule here. So start with the first function here, derivative of the first function, derivative of e to the sine x. Well, actually, we just did that. So we should be able to do it again. It's a composite function, so follow chain rule. It's e to some power. It's derivative of the outside. Chain rule says you substitute in the inside function next, sine of x. And then finally, we multiply that by the derivative of the inside, which is cosine of x. We then multiply that by the second function. All right, be careful that you understand that this cosine of x, that first cosine of x that showed up, was all from the derivative of e to the sine of x. And that the second cosine that shows up is the second function there. It's easy to leave off one of those and obviously get the wrong result. We're still not done, though. That's only the derivative of the first function times the second. I then have to add that to the first function, e to the sine x, times the derivative of the second function. Derivative of cosine is a negative sine of x. Put that in parentheses there because it's got the negative sign there. There's our second derivative. Let's just rewrite this here slightly. So I've got e to the sine of x. Cosine times cosine could be written as cosine squared x plus e to the sine x. Actually, I should make that a minus because of the negative that I've got in front of the sine over there. So I'll make it minus e to the sine of x times the sine of x. That would be a way that I could rewrite that. In fact, if you wanted to, because I see that I have a factor of e to the sine x, similar to what we did in the last problem. Sometimes the book will do this. I could factor out that e to the sine x and get e to the sine x times cosine squared x minus the sine of x. Would be another way to rewrite that. Again, you don't need to go to that step. If you leave it right here in this form right here, you're all set. But if you want to see if how the book got their answer, they might go to this next step and write it in that factored form. All right, one last thing for us to look at here is what happens if we extend this beyond two functions, which is what we've been working with. What if it's the product of three functions? And for that matter, if we extended it even further to more than three functions. So if it turns out that you've got the product of three functions, let's say we call those three functions u, v, and w. If y is equal to u times v times w, then y prime is equal to u prime times v times w plus u times v prime times w plus u times v times w prime. In other words, what it turns out there is we have y prime is equal to the derivative of the first function times the other two, plus the derivative of the second function, v prime, times the other two, plus the derivative of the third function, w prime, times the other two. And actually reading it off in that way allows us to extend this in a more general form. What if we have the product of n functions? So in that case, if y is equal to, let's say, z1, z2, z3, all the way up to z sub n are our n functions, if y is equal to the product of z1 times z2 times z3 and so forth, all the way up to z sub n, then y prime is equal to the derivative of the first function, z1 prime, times the other functions, plus the derivative of the second function, z2 prime, times all of the other functions, plus the derivative of the third function, z sub 3 prime, times all of the other functions, plus, and so forth, all the way up to the very last one, which is z1, z sub n prime, times the other functions. So there's the generalization of that. In fact, I should have a dot, dot, dot in here. Let me just add that in to indicate that this pattern continues. And there's our generalization. So in other words, you end up with the sum of n derivatives there when you get done. There's n things that you're adding up there, and you're multiplying each of those derivatives by the other functions. All right, that is the end of this section here for us.